what is really inside the sun. Today, let's set our course for the incandescent heart of our system, the sun. Immense, blinding, vital, yet still mysterious. Beneath its fusion surface, an inferno of pressure and plasma gives birth to titanic energy. A nuclear core where each second, millions of tons of hydrogen become light. But the interior of the sun is not just a furnace. It's a code yet to be deciphered. A fragile balance between explosion and gravity. And if by uncovering its secrets, could we finally understand what keeps the universe alive? But before embarking on a new adventure, remember to like the video and subscribe to the channel so you don't miss anything. Thank you and bon voyage. From our vantage point on planet Earth, our gazes turn to the sun, this incandescent sphere that has surrounded us for billions of years. Yet, despite its familiarity, it still harbors many mysteries. In this section of our Odyssey, we will progress step by step toward this fiery star, first passing through two essential stops, Venus and Mercury. They will help us understand the force of gravity, the power of the solar wind, and how space exploration brings us slowly but surely closer to the impossible, touching the sun's surface. Prepare to uncover the unknown. First stop, Venus, often called Earth's twin sister. Although its diameter is close to ours, it is enveloped in a thick atmosphere of carbon dioxide, where the surface temperature reaches about 460 degrees Celsius or 860 degrees Fahrenheit. This furnace, maintained by an intense greenhouse effect, creates pressure such that a human could not survive there for more than a few moments. For probes like Parker's Solar Probe, Venus plays a crucial role. Thanks to 7 gravity assists conducted between 2018 and 2025, the probe has gradually reduced its orbit around the sun. In 2024, a major discovery was made in Venus's upper atmosphere. Gravitational waves were detected. They arise from the interaction between planetary gravity and the planet's rotation, causing disturbances that propagate through the gas layers. Surprisingly, this phenomenon shows similarities with what scientists observe in the solar corona. This unexpected analogy suggests that Venus, despite its stifling atmosphere, could enlighten us on some complex solar mechanisms, particularly on the heating of outer layers. Venus has always held a strategic place in the history of astronomy. During the transits of 1761 and 1769, astronomers around the world observed the planet crossing the sun. By measuring the exact duration of these passages from different points on Earth, they were able to calculate the distance separating our planet from the sun. From this was born the astronomical unit, close to 150 million kilometers or 93 million miles, a major scientific achievement that paved the way for international collaborations in astronomy. We now leave behind the clouds of Venus to reach Mercury, the closest planet to the sun. Bombarded by the solar wind, it only possesses an extremely tenuous exosphere, formed of atoms stripped from its surface by these high-energy particles. In some places, hot poles are visible, revealing surprising irregularities in its thin magnetosphere. Unlike Venus, Mercury does not have a protective atmosphere. It undergoes extremes of heat and cold, as well as direct exposure to solar particles. NASA's Messenger mission and the European and Japanese space agencies' Bepi-Colombo mission have shown how exposed Mercury is to the solar corona. By studying the variations in speed and density of the solar wind, they have traced the signatures of slow and fast flows to the planet's twilight regions. The absence of an atmosphere means that, just as the sun's corona does not have a solid surface, Mercury hardly filters anything. Matter and magnetic fields circulate freely there, offering a natural laboratory for understanding the solar environment. After these two planetary stops, the most daring moment approaches, diving towards the Sun. In August 2024, Parker's solar probe reached a perihelion of about 3.8 million kilometers, or 2.4 million miles, above the photosphere, approximately 5 times the solar radius. At this distance, the temperature of the corona exceeds 1,000,000 degrees Celsius, or 1.8 million degrees Fahrenheit, but many parameters of plasma dynamics remain unknown. Why is the corona so hot when the surface reaches only 5,800 degrees Celsius, or 10,572 degrees Fahrenheit? At the heart of this infernal zone, Parker's solar probe observed strange reversals of the magnetic field, called switchbacks. These inversions appear as sudden changes in direction in the force lines, akin to a whipped rope. Researchers believe these switchbacks release stored energy, thus contributing to maintaining the corona at a temperature much higher than that of the photosphere. Understanding this phenomenon could solve one of the greatest enigmas of heliophysics. Why is the solar atmosphere hotter than the surface? Following Parker's solar probe virtually, we observed the dance of solar particles launched at several hundred kilometers, or hundreds of miles per second. Through this flow, we fly over the polar plumes of the corona, discover dark coronal holes, and perceive micro-eruptions, sometimes called campfires, highlighted by solar orbiter in extreme ultraviolet light. Each tiny flare releases a torrent of energy, likely involved in coronal heating, even if the exact process remains to be elucidated. For centuries, humanity has been fascinated by this luminous halo surrounding the sun during total eclipses. Medieval Arab astronomers already described the white hair-like structure rising around the masked solar disk, an almost mystical spectacle. In 1715, Edmund Halley, dazzled by the filamentous silhouette of the corona, engraved his observations to share this discovery. These historical testimonies bear witness to the emotion stirred by the corona long before the era of space probes and modern instruments. Now, let's cross a threshold. Carried by coronal jets exceeding 500 kilometers, or over 300 miles per second, we plunge into the sun's infernal hairdo. There, the matter is no longer solid or gaseous, but presents itself as hot plasma, where protons and electrons evolve within intertwined magnetic fields. This boiling zone remains an enigma, as its complex dynamics still elude our models. Yet, it is precisely by penetrating it that we hope to unravel age-old mysteries, including the origin of the solar wind. The adventure takes shape. We enter the corona to begin our deep exploration. To withstand this intense heat, Parker's solar probe is equipped with a carbon heat shield. However, it is necessary to distinguish between temperature and energy flux. Despite the extreme heat of the corona, the plasma density is so low that the amount of heat absorbed remains limited. In other words, the shield acts like an umbrella, protecting the probe's instruments while allowing some sensors to be exposed to gather essential data. To reach this perilous orbit, it takes advantage of gravitational maneuvers around Venus. At each flyby, the probe adjusts its speed and trajectory thanks to the planet's gravity, reducing its orbit in several stages. This technique avoids depleting significant fuel reserves by using Venus's gravitational forces to approach ever closer to the Sun. The unprecedented data collected should one day enable scientists to accurately predict large-scale solar storms. The reversals of the magnetic field, shockwaves detected in the Venusian atmosphere, and Mercury's frontal exposure to the solar wind are all clues to better understand the interactions between our star and the celestial bodies orbiting it. In the future, this knowledge will help protect our satellites and power grids from solar eruptions. From ancient observations of Venus to contemporary missions, Our steps toward the sun are only getting closer. This epic journey, starting from Earth, leads us by Venus and Mercury before plunging us into the arms of the sun. Each step reveals a fragment of truth about the universe, encouraging us to relentlessly continue space exploration. From the confines of the Earth's high magnetosphere, imagine yourself floating silently in space, far from earthly hustle and bustle, to contemplate the immense solar disk. From here, the brightness is already of an almost dazzling intensity. The Earth, tiny below, benefits from the protection of its magnetic field. But we are about to leave this refuge to gradually enter the vast interplanetary plains, where solar particles trace almost invisible trails. Our goal is to unravel one of the most fascinating enigmas of solar astronomy, the corona, this mane of the sun, vibrant with a ballet of plasma and magnetic lines. Before embarking on this odyssey, let's set the scene. At the visible limit of the sun, the photosphere, the temperature reaches about 5,800 degrees Celsius, or 10,400 degrees Fahrenheit, already unimaginable for any terrestrial material. Yet, as we ascend into the upper layers of the solar atmosphere, the temperature skyrockets to over 1 million degrees Celsius, or 1,800,000 degrees Fahrenheit, or more. This paradoxical inversion defies logic. Instead of cooling as it moves away from the heat source, the gas heats up at altitude. Physicists call this the coronal heating paradox, and have been questioning the source of such thermal escalation for decades. To shed light on this mystery, numerous space missions and ground observations compete in sophistication. Among them, Parker Solar Probe, launched by NASA, approached the sun closer than any other probe. In 2024 and 2025, it broke the record by positioning itself at only 3.8 million kilometers, or 2,360,000 miles from the solar center, an incredibly short distance on a stellar scale. There, the corona proves to be a furnace at several million degrees Celsius, and the probe's instruments captured astonishing signals in the particle wind. Among these observations are the mysterious switchbacks, sudden reversals of the magnetic field, which manifest as abrupt bounces of the force lines. It is imagined that by thus distorting the magnetic flow, these switchbacks transfer energy to the plasma, helping to heat the corona to extreme temperatures. In parallel, Solar Orbiter, a joint mission of ESA and NASA, has provided complementary insights thanks to its extreme ultraviolet cameras. This instrument has unveiled numerous microeruptions, nicknamed campfires. Invisible from Earth with conventional means, these small flares occur continuously on the solar surface, and each release a significant amount of energy. On the scale of an extended region, their thermal contribution could add up to keep the corona at each of its layers at temperatures defying any explanation by simple conduction from the photosphere. Beyond these discoveries, the corona can be admired during total eclipses. When the moon masks the solar disk, this whitish halo, reminiscent of an ethereal mane, becomes visible. Arab scholars of the Middle Ages already described it as a white mane floating in the sky. Later, in 1715, the astronomer Edmund Halley, dazzled by this filamentous structure, published his engravings detailing its multiple fibers and rays. These accounts illustrate the fascination the corona held long before the advent of probes and modern instruments, capable of studying it up close. It should be noted that the corona is not homogeneous. Various types of structures linked to the magnetic configurations of the sun can be distinguished. There are coronal holes, areas where the magnetic field opens out into space, allowing the solar wind to escape at high speeds. These holes mainly appear at the poles, forming escape routes for the plasma as the sun enters certain phases of its cycle. Conversely, luminous loops, often spectacular, trap coronal plasma in magnetic arcs, delaying its cooling and contributing to potential coronal eruptions, subsequently releasing particles capable of impacting the solar environment up to the planets. Polar plumes are also observed, rising above the solar poles like fine, luminous columns. These plumes testify to emerging magnetic fields that catalyze the plasma, accentuating the distinction between fast and slow solar winds. Each of these structures plays a role in the corona's overall dynamics. Some channel the fast wind, others confine the plasma to heat it. To probe this scorching crown, researchers today deploy instruments of extreme precision. For instance, the Daniel K. Inouye Solar Telescope in Hawaii uses spectropolarimetry to analyze signals emitted by different chemical elements, deducing the velocity, density, and magnetic state of the particles. In space, the coronagraphs of the Solar and Heliospheric Observatory, SOHO, notably those in the LASCO series, occlude the photosphere to reveal the diffuse brightness of the corona. Finally, networks of radio telescopes like LOFAR in Europe map low-frequency emissions, tracing the interactions between the solar wind and the corona. By uniting these observations, scientists obtain a multi-dimensional view of the solar atmosphere. And yet, despite these advanced tools, many questions remain open. Why do we so often observe these switchbacks? What exact role do micro-eruptions play in the overall energy balance of the corona? Could the magnetic waves known as Alfvén waves, which propagate in plasma interacting with magnetic fields, transport enough energy to maintain the corona at millions of degrees? No definitive answers have been provided yet. Scientific debates persist, mobilizing numerical modeling, high-resolution observations, and synchronized campaigns in a collective quest to solve the enigma of coronal heating. Since time immemorial, the observation of the corona has inspired awe. Back when one patiently awaited eclipses to glimpse its luminescent mane, astronomers described this halo as a quasi-mystical phenomenon. Today, thanks to space telescopes and solar probes, we can study it without waiting for these rare events. The ultimate goal remains to elucidate how the photosphere, already at 5,800 degrees Celsius, 10⁻⁷72 degrees, releases a corona capable of reaching several million degrees Celsius, multiply by 9 to 5 and add 32 to convert. Solving this mystery would illuminate not only stellar physics, but also the impact of the solar wind on the entire solar system and beyond, shaping the heliosphere over hundreds of millions of kilometers, miles. After so many historical and contemporary discoveries, the time has come to dive towards the Chromosphere, the immediate neighbor of the corona. Carried by coronal jets at more than 500 kilometers per second, 310 miles per second, we would feel the power of the solar magnetic field like a torrent sweeping everything in its path. Researchers studying the transition between the corona and chromosphere invite us to cross this zone, a glowing ocean where the temperature is around 10,000 degrees Celsius, 18,032 degrees, to discover how coronal plasma transforms before reaching the surface. The chromosphere extends just above the photosphere, like a glowing ocean streaked with incandescent waves and jets of matter. It has no defined surface. It's a thin layer of the solar atmosphere, situated between the cooler photosphere and the much hotter corona. To discover it, imagine navigating this incandescent medium, studying its unique phenomena, and grasping its essential role in the solar machine. Let's start with its particularly distinctive hue, which gives it the name color sphere. During a total eclipse, it appears as a reddish ring around the masked sun. This color primarily comes from hydrogen alpha emission. When the hydrogen atom changes state, it emits a bright red light. Given the richness in hydrogen of this layer, it radiates abundantly in this red light when the solar disk is eclipsed by the moon. Historically, this red hue aroused great curiosity. In 1868, Norman Lockyer and Jules Janssen observed, during an eclipse, new spectral lines in the chromosphere. They then discovered a new gas on Earth, which they named helium, from the Greek helios for sun. At the time, the existence of elements beyond our atmosphere was unknown, and this discovery proved that the sun harbored chemical signatures capable of revealing new elements. It remains today a formidable natural laboratory for studying matter under conditions impossible to reproduce on Earth. The chromosphere offers a unique field of study for understanding the interaction between solar layers. Far from being calm, it is full of dynamic structures like spicules and fibrils. Spicules, these vertical jets of plasma, rise 5 to 10,000 kilometers, or 3,107 to 6,214 miles, before falling back or transforming within a few minutes. Fibrils, close relatives of spicules, take on more elongated shapes, sometimes dark or bright, depending on the angle of view and the wavelength used. These structures illustrate the beauty and complexity of the chromosphere. They reveal the presence of Alfvén waves, magnetohydrodynamic waves that, like waves along an elastic string, transport energy along magnetic field lines. These waves likely contribute to the heating of the upper layers, but it remains a challenge to understand why some dissipate their energy in the chromosphere while others reach the corona. Over the years, thanks to ground-based telescopes and space missions, we have understood that spicules and fibrils are not just a spectacle. They could transfer matter and energy from the photosphere to the corona. However, the latter, hotter than the visible surface, reaching several million degrees, represents a paradox. While the photosphere peaks at about 5,100 degauss or 10,472 degauss, the chromosphere itself ranges from a few thousand degrees to its base to tens of thousands at higher altitudes, thus playing an intermediate role in the spectacular rise in temperature. Recent observations conducted until 2024 confirm the importance of this area. The Solar Orbiter probe, equipped with the Extreme Ultraviolet Imager, EUI, has detected small plasma jets called jetlets at the solar poles. Narrower than regular spicules, these jetlets frequently emerge and could provide the necessary energy to supply the chromosphere and corona with heat and particles. These discoveries seem linked to the phenomena observed in the solar wind, notably the switchbacks, sudden reversals of the magnetic field in this particle flow. It is assumed that the polar jetlets could contribute to these magnetic inversions detected in orbit around the Sun. Even if the mechanism is not yet elucidated, the temporal correlation between these plasma eruptions and the irregularities in the solar wind offers new research avenues. Several techniques are essential for observing and analyzing these phenomena. Spectral observation allows mapping variations in temperature, density, and magnetic fields. The study of the ionized calcium K-line, known as calcium 2K, functions as a beacon. By decomposing the light, one observes shifts towards the blue or red, revealing plasma movements due to the Doppler effect and thus measuring its speed. Analysis of asymmetry in spectral lines is also used. Absorption or emission profiles can present a shifted peak, indicating that different layers are moving at varying speeds. These shifts indicate complex dynamics, such as waves circulating at various levels or plasma jets rising and descending simultaneously. Space telescopes, such as IRIS, Interface Region Imaging Spectrograph, offer remarkable precision. By targeting the transition between the photosphere and chromosphere, then between the chromosphere and corona, IRIS captures high-resolution data over a few seconds, allowing tracking of the evolution of spicules and fibrils in real time. These observations are crucial for understanding how magnetic and kinetic energy transforms into heat, in other words, for solving the solar heating problem. Furthermore, what happens in this glowing zone directly influences the corona. The chromosphere acts as a filter. It regulates the passage of particles and magnetic energy from the solar surface. When thinking about the solar wind, it is often forgotten that these particles originate in the lower layers, heat up, and escape via the chromosphere. That is why many models predict that chromospheric activity conditions the intensity and structure of the solar wind. By immersing ourselves in this glowing ocean, we quickly understand that everything is governed by magnetic fields. In the chromosphere, the gas is sparse enough for the magnetic field to deeply influence the movements, while the plasma pressure remains higher than that of the corona. Thus, arches, loops, and sometimes gigantic prominences arise at the chromospheric boundary, giving the sun a spectacle that ground-based observers have been attempting to decipher for decades. Some new-generation ground-based telescopes, like the Daniel K. Inouye Solar Telescope in Hawaii, achieve a resolution of about 20 kilometers or 12 miles. By analyzing the light in hydrogen alpha and the ionized calcium K line, researchers create a true film of chromospheric turbulence. From 1 minute to the next, we see waves, jets, eruptions, or granulation extending into the upper layers. Understanding the transition to the photosphere below is just as fascinating. The chromosphere, located above the photosphere, sees its temperature increase with altitude. This thermal gradient, sometimes modulated by the magnetic field, ranges from nearly 5,800 degrees C or 10,472 degrees F in the photosphere to over 10,000, 20,000, or even 100,000 degrees C or 18,032 degrees F at the gateway to the corona. When we dive below the wave carpet, we leave the base of the chromosphere to reach the photosphere. Here, the gas is denser, even though it is still thinner than terrestrial air. The granulation cells, vast bubbles of hot gas, form and dissipate quickly. In altitude, in the chromosphere, the energy transport becomes more complex. The incandescent vapor is agitated by magnetic tensions, and waves make it ripple like marine crests. This final dive below the chromosphere heralds the discovery of a more familiar surface of the sun, where dark spots, bright granules, and giant matter ejections appear. The chromospheric boundary is a key point. It separates a still relatively dense and partially ionized plasma from the corona, where an extremely tenuous and overheated plasma reigns at several million degrees. New observation campaigns, notably those planned for 2024, with the EUI instrument, promise to clarify our understanding of these processes. Astronomers seek to elucidate the links between chromospheric eruptions and solar wind disturbances, such as the mysterious switchbacks. They also want to grasp how magnetic energy is channeled or dispersed across the chromosphere to ultimately explain coronal heating. At the end of this exploration, we find ourselves at the boundary of the chromosphere, ready to descend towards the photosphere, more familiar to observers. Crossing this threshold is to touch the layer where most of the visible light that illuminates our sky is born. Behind us, the chromosphere stretches with its jets and red streaks, a vibrant plasma ocean that we leave with regret. as it still holds many mysteries. But the adventure continues towards the photosphere. In summary, the chromosphere is a gateway between the lower solar layers and the corona. One cannot explore it without admiring its boiling, studying its plasma jets like celestial geysers, or measuring the historical importance of its discoveries, such as that of helium. It remains a theater of revolutionary observations that transform our view of the sun and stars. The next step of our journey awaits us in the photosphere, where we will descend towards a region less hot than the chromospheric summit, but just as fascinating. By diving below this red wave carpet, we will leave behind spicules and swirling waves to explore the dense layer where convective granulation is born, feeding the chromosphere with its energy. Descending into the photosphere is to penetrate the origin of the convective movements that propel solar magic to the corona. We thus leave the glowing ocean of the chromosphere, not without a last amazed glance at its complexity. This moving mantle, invisible in white light, remains essential for understanding why the solar atmosphere peaks at several million degrees, while the photosphere reaches only a few thousand degrees. With each technological advance, we discover finer structures and move forward in understanding the fundamental forces that agitate our star. Thus continues the great journey to the depths of the sun. The chromosphere, although discreet to those who only see it during an eclipse, turns out to be an intense transition zone. Its pyrotechnic feats, observed by increasingly powerful ground and space telescopes, enrich our overall view. Get ready to cross the next frontier, where visible light bursts forth, the photosphere. Here, we will leave behind the ardor of the spicules, the dance of the fibrils, and the rumble of alpha waves to scrutinize the signs of even deeper magnetic activity. Here we are at the end of this part of our adventure. We leave the chromosphere to begin the chapter of the photosphere. Under this reddish mantle, another landscape awaits us, made of bubbling granules and magnetic loops that trace the thread of solar evolution. But let us keep in mind the radiant beauty of the chromosphere, this kingdom where, a few thousand kilometers, or miles, immense energy dramas play out. Ongoing research, strengthened by future data from 2024, will continue to unravel the mysteries of this fascinating world and answer one of the great secrets of solar physics. How does the sun transform its internal energy into an iridescent breath that nourishes the entire solar system? For many, the sun is just this dazzling disk that rises and sets without us perceiving its true complexity. The visible part is called the photosphere, a Greek term meaning luminous sphere. It is not a rigid surface like on Earth, but a layer of very hot and relatively dense gas, opaque enough to trap light before sending it back into space. It is what our eyes see as the boundary of the sun. Less hot than the corona, but hotter than anything on Earth, the photosphere is not uniform. It forms a constantly moving mosaic, granulation. Imagine the surface of a pot of boiling water, except here, the fluid is ionized plasma. Thousands of cells are constantly boiling to transport heat and matter. These granulation cells, hundreds to thousands of kilometers or miles wide, live for a few minutes before disappearing, giving way to others. You would see them rise and fall like popcorn grains if you could zoom in enough. Each cell corresponds to the top of a convective column. Hot gas rises, then, as it cools, falls back around the periphery. To study these changing patterns, astronomers rely on the Daniel K. Inouye Solar Telescope in Hawaii. Its imposing mirror and exceptional sharpness of vision allow distinguishing minute details in the photosphere. Thanks to it and other observatories around the world, the solar dynamics are reconstructed with unprecedented precision, shedding light on the journey of energy from the sun's core to its surface, and then into space. Among the most spectacular phenomena are sunspots. These dark regions, often larger than Earth, arise where the magnetic field pierces the surface. The magnetism is so intense that the plasma, slowed, cools locally, making these zones darker, although they still emit a lot of energy. Sunspots follow an activity cycle that rises to a peak and then falls. We are currently heading towards a new peak, expected in the coming months. At that time, the number of sunspots increases, sometimes in large complexes, and the sun then emits more intense eruptions and particle jets capable of influencing the Earth's environment. Hence, the particular attention paid to them by the scientific community. A recent discovery has highlighted very fine structures related to sunspots, called dark fibrils. These are thin plasma filaments, stretching within active zones and perhaps beyond. Their exact origin remains debated, but they could play a role in transferring magnetic and thermal energy to the upper layers. New observations and detailed simulations are underway to shed light on their function. When observing the photosphere, it is also noticeable that the sun does not rotate like a rigid body. The equator rotates faster than areas near the poles. This differential rotation tangles the magnetic field lines and generates the sunspot cycle. Without this phenomenon, the solar magnetic dynamics would be much simpler, and activity would vary much less from year to year. The study of the photosphere dates back several centuries and was marked by a famous controversy between Galileo and Christoph Scheiner. Galileo argued that the spots were present on the surface of the sun, while Scheiner initially thought they were objects transiting in front of the star. Challenging the idea of a perfect sun sparked a genuine intellectual frenzy, fueling the rise of solar astronomy. A key milestone occurred with the first photographs of the sun, taken at the dawn of photography. Thanks to inventor Louis Daguerre, astronomers could immortalize the surface without relying on drawings, paving the way for modern solar photometry and spectroscopy. The ability to preserve an accurate image revolutionized astrophysics. Today, the analysis of the photosphere goes beyond merely identifying spots. Filters and instruments are used to probe various depths, measure plasma movements, and map the magnetic field. Technological advancements, along with the proliferation of terrestrial and space telescopes, allow the detailed study of energy paths and magnetic structure. At the same time, supercomputers simulate these processes with ever-increasing realism. If one imagines the photosphere as an ocean, it is constantly agitated by convection and magnetic forces. The granules and spots are the waves of this incandescent sea. Beneath it, solar matter bubbles in the convective zone, supplying energy to the visible surface. The next step in this exploration is to delve beneath these granules, to study the convective zone, where the incessant movements of plasma shape solar dynamics. The convective zone of the sun is a place of incessant movements and intense energy exchanges, nestled below the visible surface and extending up to 200,000 kilometers or 124,274 miles in depth. Imagine yourself in an ocean of boiling plasma, responsible for bringing up the energy produced lower down, in even hotter and denser regions. In this vast envelope, the matter has cooled sufficiently for photons, previously responsible for energy transport in the radiative zone, to no longer play that role alone. Throughout this chronicle, we will explore every detail of this convection phenomenon and see why it so fascinates scientists, particularly through the study of pressure waves and the identification of giant whirlpools 50,000 kilometers or 31,068 miles in diameter. Let yourself be guided into the heart of this plasma river, where everything mixes in an incessant ballet. To better understand the convective zone, one must first grasp that energy circulates there mainly through the movement of matter itself. Inside the Sun, thermonuclear fusion in the core generates the initial energy. As one moves away from this core, the radiative zone is traversed, where photons bounce around for tens or hundreds of thousands of years. Then, temperature and density gradually decrease, making the plasma more opaque. At this stage, photons can no longer efficiently transmit their energy. The plasma then enters convection, like a boiling liquid, with hot fluid bubbles rising, cooling at the surface, and then descending endlessly. This analogy provides a glimpse of the large-scale convection mechanism in this region, 200,000 kilometers, or 124,274 miles thick. To give you a sense of scale, convection cells come in several categories. On the surface, granulation consists of cells about 1,000 kilometers or 621 miles in diameter, giving the photosphere a leopard skin appearance through the telescope. Just above, mesogranulation consists of cells several thousand kilometers or miles wide, while supergranulation extends over several tens of thousands of kilometers or miles. These hierarchical levels of convective currents interlock like Russian dolls, each playing a role in the overall heat transport. The deeper one goes, the more these cells become gigantic and their lifespan lengthens. Studying the interior of the Sun without sending a probe requires a fascinating discipline, heliosismology. This involves observing pressure waves, or pressure modes, on the surface that travel through the solar interior. The convective zone teems with vibrations, like a cosmic musical instrument constantly excited by turbulent movements. Each mode of vibration corresponds to a specific path taken by the wave through the internal structure. By measuring the frequency, amplitude, and dispersion of these waves on the surface, it becomes possible to reconstruct the internal map of velocities, density, and temperature of the plasma in the convective zone. Similar to terrestrial seismology, where seismic waves reveal the Earth's internal composition, heliosismology unveils the structure and dynamics beneath the photosphere. By carefully studying the spectrum of waves, researchers reconstruct in 3 dimensions the speed of meridional currents and the distribution of areas where the plasma rises or falls. Thanks to heliosismology, major discoveries have punctuated our understanding of the convective zone. Between 2023 and 2024, the Global Oscillation Network Group, GONG, a network of ground-based solar observatories, confirmed the existence of giant plasma vortices, sometimes called giant vortices. These swirling structures extend over 50,000 kilometers, or 31,069 miles in diameter, exceeding the size of Earth. These vortices evolve and interact in an already very agitated environment where magnetic fields constantly fluctuate. Their identification was made possible thanks to the fine analysis of signals recorded in near real time by several stations distributed around the planet, avoiding losing sight of the Sun due to Earth's rotation or weather conditions. Researchers sometimes compare these vortices to giant cyclones. Just like on Earth, differences in pressure and temperature create swirling movements. But here, it's the magnetic and thermal variations of the plasma that govern the formation of these colossal patterns. Why are these vortices, as well as the entire convective zone, crucial for understanding solar behavior? One of the primary reasons lies in the solar dynamo, the process by which the Sun generates and regenerates its own magnetic field. The magnetic field profoundly influences surface activities such as sunspots, flares, or even the solar wind. It conditions the intensity of activity cycles, which oscillate over 11 years, as well as the shape and extent of the solar corona. However, the dynamo arises from the combination of the sun's differential rotation, faster at the equator than at the poles, and the perpetual stirring of plasma in the convective zone. As magnetic field lines are buffeted by convection, they lengthen, twist, and rearrange, strengthening or annihilating at certain points. This complex dance of twists generates the magnetic phenomena observed on the surface. Without this convective turbulence, the sun would not have the same magnetic personality, and its activity would certainly be more monotonous. To popularize the convection occurring in this region, some scientists compare the plasma to a flowing river. Replace water with an ionized mix of hydrogen and helium heated to several thousand or million degrees, and imagine a river several tens of thousands of kilometers or miles wide. This plasma reacts to changes in temperature, density, and especially to the influence of the magnetic field. Inside the sun, these parameters change rapidly, and convection is constantly reorganizing. Sometimes, a faster flow will collide with a slower flow, creating intense turbulence. The recently detected giant vortices testify to these interactions and the phenomenal energy exchanges that result from them. As we follow this narrative, we can already glimpse the future. The deeper we go, the more the differential rotation strengthens, and the more these solar layers are enriched with magnetic energy. At the lower boundary of the convective zone lies the Tachocline, a shear boundary where the rapid rotation of the radiative zone meets the differential rotation of the convective zone, creating a notable velocity gradient. In this thin layer, modest in thickness on the solar scale, it is here that, according to many magnetohydrodynamic models, the large magnetic cycles of the sun are forged. The Tachocline acts as the hinge of the dynamo. It is at this location that magnetic field lines are kneaded, stretched, sometimes broken, or recombined, giving rise to new magnetic configurations that will emerge on the surface as sunspots, sudden eruptions, or bright loops in the corona. Before reaching this boundary, let us remind ourselves that within the convective zone, the matter remains in an extremely hot and partially ionized state. Electrons separate from some of the hydrogen or helium nuclei, giving this fluid a particular behavior. It becomes conductive and interacts with the magnetic field, bending or pushing the magnetic lines to curve around it. This mutual interaction between matter and magnetism gives the impression of a moving fire where everything is connected. Hence the importance of precisely studying the speeds, turbulences, and density distribution in this region. Today, scientists have several techniques to probe the convective zone, the most famous of which remains heliosismology, already mentioned. But other complementary methods exist. Photosphere spectroscopy, for example, provides information on the quantities and speed of elements such as iron or calcium. Long-term observation campaigns are conducted using space telescopes and synchronized ground networks such as GONG or other projects. The objective is to obtain a near-continuous monitoring of solar activity to detect the slightest unusual oscillation and derive new information from it. Every disturbance on the surface can be the signature of an internal phenomenon in the convective zone. Researchers therefore relentlessly scrutinize the dance of the sun, and it is this persistence that has confirmed the existence of giant vortices. Today, a line of study seeks to determine whether these whirlwinds directly influence the intensity of the regional magnetic field, or if they quickly dissipate in this incessant furnace. The incessant churning of the convective zone illustrates another key point. While the radiative zone ensures a stable transport of energy by photons, the convective zone is the scene of agitation that conditions the very appearance of the sun on the surface. Without convection, The photosphere would not exhibit its characteristic granulation, and sunspots, linked to concentrated magnetic fields, would not form in the same way. It is this remarkable dynamic that gives the sun its ever-changing face, despite its overall stable appearance. On a larger scale, this churning also influences the magnetic activity cycle. Even modest variations of this cycle modulate Earth's spatial environment. This shows how crucial the convective zone is to understanding the phenomena that eventually affect us, such as coronal mass ejections or solar storms, which can disrupt radio communications or cause electrical surges. By exploring this region, we have therefore understood the importance of heliosismology for mapping plasma movements, how convection feeds the solar dynamo, and the discovery of giant vortices confirmed by observation networks. The convective zone, with its hierarchy of granulation, mesogranulation, and supergranulation, is an essential cog in the solar machine. It acts both on energy transport to the surface and on the churning of the magnetic field in this vast expanse. As we approach the Tachocline, we prepare to discover another key region where the uniform rotation of the radiative zone meets the differential rotation of the convective zone, generating magnetic couplings of great complexity. It is precisely towards this shear boundary that we will now direct our gaze. In the Tachocline, everything occurs within a thin range of depth, but the consequences on the magnetic cycle and the birth of spectacular surface phenomena are enormous. For now, retain the image of an interior river, swirling and incandescent, carrying energy from the bottom to the top, modified by the magnetic fields it crosses and emerging more or less deformed. This flow of moving matter is the origin of the cyclic variations observed on the surface of the sun and guides numerous events that eventually affect us on Earth. The adventure does not end there. In the continuation of our journey, if we could follow it, we would dive beneath this interface of the Tachocline to understand how these rotational shears give rise to the solar dynamo. But that will be the subject of another chapter, as we have just left the tumultuous river of the convective zone. Here we are at the edge, ready to cross this sheer boundary that marks the end of our journey through the convective zone. Upon entering there, we will leave this agitated and boiling universe for a more uniform rotation regime in the radiative zone. The voyage will remain exciting, for it is precisely here that the fundamental links between matter and magnetism are forged, shaping the very personality of our star. There is still much to explore and understand, but now you have grasped the vital role of the convective zone in the deep breathing of the sun. It feeds its surface and radiation while orchestrating the complex movements of its magnetic field. Day after day, scientists record and analyze signals from this region, accumulating data to refine our models and gradually unravel the fabric of this gigantic thermal and magnetic machine that is our star. Thus ends this stage of our grand journey through the sun, focused solely on the convective zone. You have imagined these plasma currents, thought about these gigantic vortices swirling like underwater solar storms, and understood how heliosismology allows us to decipher the architecture of these hot, turbulent flows in depth. Ready for what's next? Head towards the Tachocline, a key region where the magnetic history of the sun is still being written, nourished by the convective whirlpool ceaselessly beating under our eyes, immutable and changing at the same time. The solar river never stops flowing, and there is still so much to discover. The Tachocline is a fascinating boundary region inside the sun because it forms a crossroads between two zones with very different characteristics. Above, the convective zone, and below, the radiative zone. Its recent discovery has allowed for a better understanding of the remarkable mechanism that generates and maintains the solar magnetic field. Let's imagine we gradually descend through the solar layers. After passing through the convective zone, stirred by enormous plasma cells, we arrive at this decisive thin layer, whose thickness represents only a few hundredths of the solar radius, or about a few thousand kilometers, which equates roughly to a few thousand miles. Just a few hundredths are enough to harbor dynamic processes of phenomenal power. To understand why the Tachocline is fundamental, let us remember that the Sun does not rotate like a rigid solid. In the convective zone, which extends roughly from the visible surface to 70%, 43 miles, of the solar radius towards the interior, the rotation is said to be differential. The equator turns faster than the higher latitudes. Below, in the radiative zone, the rotation is almost uniform, with almost no dependence on latitude. Between these two opposing dynamics, a strong rotation gradient appears. This is where the Tachocline is located, acting as a shear boundary. This difference in speed transforms kinetic energy into magnetic energy, making the Tachocline the main seat of the great solar dynamo, that is, the set of magneto-hydrodynamic processes responsible for the appearance and evolution of the global magnetic field. To grasp the concept of the dynamo, one must briefly mention magneto-hydrodynamics, which studies the interaction between a conducting fluid and a magnetic field. In the Sun, this fluid is a plasma, a gas so hot and ionized that its particles carry electric charges. This plasma drags the magnetic field lines in its movements, while the magnetic field imposes constraints on the plasma's circulation. In the Tachocline, this interaction reaches an extreme degree. On one hand, the radiative zone rotates almost like a solid, and on the other, the convective zone rotates variably from the equator to the poles. The term shear describes this abrupt change in speed over a short distance. Over the decades, researchers have developed various theoretical models to describe these rotating ionized fluids. The magneto-hydrodynamic equations, particularly complex, can now be explored thanks to supercomputers. When referring to three-dimensional models, it pertains to simulations that consider rotation, turbulence, and electromagnetic influence. Starting in 2025, computing power will reach a level allowing for the integration of numerous microscopic phenomena, including Kelvin-Helmholtz instabilities, which are crucial for understanding plasma mixing in the Tachocline. Kelvin-Helmholtz instabilities arise when two fluid layers slide against each other at very different speeds. Imagine the interface between a fast-moving current and a slower fluid. Vortices form, tear apart, and then recompose into turbulent loops. In the Tachocline, these microturbulences, invisible on a large scale, mix the plasma, stir magnetic fields, and release energy. In other words, the latent energy of the rotation gradient turns into chaotic movements that feed the solar dynamo. 3D simulations now incorporate these instabilities, showing the emergence of microturbulences capable of powering the magnetic cycle while modulating its intensity. This mechanism of magnetic amplification in the Tachocline is not just a theoretical detail. It directly results in the variations we observe from Earth during the solar cycle. The 11-year magnetic cycle, known as the Schwabe cycle, is reflected in the more or less numerous sunspots. On Earth, it is known that these magnetic field variations slightly alter total solar irradiance, that is, the overall power received from the Sun. Even though these changes do not exceed a few tenths of a percent, they can, in the long term, influence climate and space weather. Solar flares, energetic particles, and electromagnetic bursts originate from the behavior of the magnetic field, and the Tachocline is one of its boiling cauldrons. The Tachocline is not just an element of the 11-year cycle. It is also thought to play a role in longer periods, such as the Great Solar Activity Minima, for instance, the Maunder Minimum in the 17th century. During these prolonged phases where spots become rare, it is assumed that an imbalance in magnetic field production at the Tachocline level may persist for several years or even decades. Specialists are attempting to replicate through global simulations what happens when the rotation gradient weakens or when certain turbulences no longer develop sufficiently to power the dynamo. Historically, it took the rise of heliosismology and computing to better understand this layer. Before that, researchers had theoretical models, but lacked sufficiently precise indirect observations to validate the Tachocline structure. Seismic waves, which travel through the sun vibrating at different frequencies, reflect or refract depending on the density and rotational speed of the inner layers. By studying the speed and trajectory of these waves, the solar rotation profile has been delineated. It was found that the radiative zone rotates almost uniformly, while the convective zone varies according to latitude. This discontinuity, very marked at 70%, approximately 43 miles, of the solar radius, is precisely the Tachocline. Its thin thickness results in a very abrupt change in rotational regime. As soon as heliosismology confirmed the existence of this sharp gradient, specialists in stellar dynamo immediately focused on the Tachocline. They saw it as the best explanation for the strength of the solar magnetic field. Differential rotation, combined with the tilt of the solar axis, can store and intensify magnetic lines until they become unstable and rearrange in the convective zone. This periodic rearrangement is reflected on the surface by the migration of sunspots between mid-latitudes and the equator over the cycle. Three-dimensional models for 2025 and beyond forecast a crucial advance: the ability to resolve the smallest spatial and temporal scales necessary to account for Kelvin-Helmholtz microturbulence. These instabilities occur at the boundary between two fluid layers moving at different speeds, which describes the Tachocline exactly. Below, nearly uniform rotation, and above, differential rotation. Small vortices sometimes roll up like waves under the effect of shear, then collapse, dragging plasma into an extremely energetic swirl. Within these vortices, parcels of plasma heat up locally, without necessarily emitting much light, but they leave characteristic magnetic signatures when the star is simulated or probed through its oscillations. This constant churning has two major consequences. First, it stimulates the dynamo. The generation of magnetic fields depends on the stretching, twisting, and folding of force lines. Like twisting a rubber band to store energy, magnetic lines accumulate energy, which they release suddenly in the form of eruptions or gradually during a realignment of the global field. Secondly, it can favor or disrupt exchanges between the radiative and convective zones, modulating how heat and energy rise outward. Beyond the magnetic aspect, the Tachocline also has a thermal dimension. At the boundary between a hotter but stable radiative zone and a cooler but constantly boiling convective zone, it experiences a notable temperature gradient. Comparing this heat to that in the photosphere or corona remains delicate because the pressure and density are very different. In these depths, the pressure is much higher than on the surface, and the matter is primarily hyperdense plasma. Temperatures, expressed in millions of degrees or millions of degrees Fahrenheit, are common. Their distribution depends on plasma density and how energy generates or dissipates heat, a complex balance where radiative diffusion, convection, and magneto-hydrodynamic phenomena clash. Many mysteries remain regarding the Tachocline. For example, its fine structure is not perfectly understood. Is it uniform at all latitudes? Are there humps or hollows due to the tilt of the solar rotation axis. What precise feedbacks maintain the magnetic field that intensifies there and the one that rises towards the convective zone? Advanced heliosismological observations, combined with space missions measuring solar light variability, help constrain theories. Each revision of opacity models or a new calculation of the solar chemical composition can change how energy is estimated to traverse the radiative zone to heat the tachocline. In the coming years, new instrumental and satellite projects promise to bring their share of discoveries. Global networks of helioseismic telescopes, capable of observing the sun 24 hours a day thanks to thoughtfully designed geographic coverage, will provide even more precise data on internal waves. Specialized supercomputers in magnetohydrodynamics will model the tachocline in detail, incorporating Kelvin-Helmholtz-type microturbulence with unparalleled accuracy. Scientists hope that by comparing these simulations to surface activity, they will determine how much the evolution of the solar cycle, and thus the variation in total solar irradiance, is sensitive to subtle changes in viscosity or speed in this crucial layer. From a narrative standpoint, one can imagine the Tachocline as a thin belt at the bottom of an ocean of convective plasma. This belt, like a strong ocean current, separates two bodies of water with different temperatures and speeds. On a terrestrial scale, we could cautiously compare this phenomenon to the meeting of a warm current with an icy body of water in the ocean, producing whirlpools and energy dissipation. The difference, of course, is that the intensity of the processes in the Tachocline surpasses comprehension. The energy involved is gigantic, the density high, and the generated magnetic field influences solar activity far beyond the visible spots on the surface. Thus, the Tachocline, although discrete, is at the heart of the magnetic and thermal regulation of the Sun. Since it serves as the mandatory passage between the different rotation of the convective zone and the nearly homogeneous rotation of the radiative zone, it acts as a grand energy transformer. The three-dimensional magnetohydrodynamic models of 2025 predict that Kelvin-Helmholtz instabilities play a decisive role in regulating this interface, which, by ricochet, influences phenomena as vast as the magnetic cycle, space weather, and the variation of the irradiance received on Earth. Of course, the exact role of the Tachocline in the long-term modulation of solar activity, whether it's the 11-year cycle or unusual activity phases, remains a vast field of research. Once we have dived into this key sector and understood how essential it is to the solar dynamo, we can continue our journey to the radiative zone even deeper. There, the sun's energy is transported mainly by photon diffusion, no longer by imposing convection bubbles. This transition is the next chapter of our inner journey. We will slip under the agitated boundary of the Tachocline, enter a space where rotation becomes uniform again, where matter is denser and calmer, and where photons from thermonuclear reactions begin a true marathon to reach the surface. Leaving the Tachocline, we realize how much this thin shear zone, coupled with extreme turbulence, is essential for understanding the magic of the sun. It acts as a conductor, setting the intensity of magnetic fields on the fiery score of solar activity. The radiative zone is one of the most fascinating stages of the journey to the solar core. Here, energy transfer no longer happens through vigorous convection, but through a slow passage of packets of light through an ocean of particles. Imagine an extremely dense and hot environment, much more compact than the region where magnetic loops are born on the surface. In the radiative zone, matter is so compressed and heated to several million degrees, or over 5 million degrees Fahrenheit, that atoms are often ionized and photons continuously interact with electrons and nuclei. The result, a photon set in motion at the beginning of this zone takes an enormous amount of time to escape. A true photonic marathon that lasts approximately 170,000 years. In other words, a photon born at the beginning of this zone bounces around on particles before reaching the boundary with the convective zone, then the solar surface. This incredible duration is explained by the very nature of radiative transport. Unlike convection, which resembles a boiling pot where hot matter rises and cold matter sinks, the radiative zone lets energy pass through photon diffusion. Imagine a very dense crowd where you can only move forward by taking small steps, constantly bumping into those around you. That's what a photon experiences: absorbed, then re-emitted in another direction, absorbed again until it progresses, bounce by bounce, toward the periphery of this immense layer. To understand why it's called the radiative zone, let's recall the distinction between the sun's internal layers. Above, the convective zone stirs plasma, producing granulation and dark spots on the surface. In the radiative zone, the density is such that matter becomes stable and can no longer move by large overturns. Energy is then transmitted almost exclusively by photons. We are in an environment bathed in intense, high-energy radiation, where multiple light diffusion dominates. Another crucial aspect lies in opacity, which refers to the ability of matter to absorb or scatter radiation. When we say that opacity depends on iron, we highlight that the presence of metals such as iron or nickel significantly influences how light passes through plasma. Even if these elements represent only a small fraction of the solar mass, they noticeably alter the absorption and re-emission of photons. Over time, astronomers regularly refine the opacity values in the opal tables, which specify the interaction between matter and light for each temperature and pressure. The 2024 revision is based on new spectroscopic measurements, allowing for a better understanding of the exact contribution of iron and other elements. Why is this essential? Because our models of the solar interior depend on assumptions about these interactions. A small error notably alters the estimates of temperature, density, and energy transport speed from the center to the surface. Beyond opacity, the radiative zone is also crucial for understanding the internal rotation of the Sun. This star does not rotate like a rigid solid. Its surface exhibits differential rotation, faster at the equator than at the poles, and other nuances emerge in depth. To probe the radiative zone, invisible in direct light, astrophysicists study gravitational oscillations, called gravity modes. These internal waves, guided by density variation and the restoring force, are distinct from cosmological gravity waves. They manifest as subtle vibrations in the deep layers. In practice, directly detecting these gravity modes is difficult because their surface amplitudes are very weak. Yet by finely analyzing variations in luminosity or other indirect signatures, researchers paint a precise picture of internal rotation. Each mode reacts to the configuration of density and temperature it traverses. By collecting enough data on these waves, the rotation speed at different depths is deduced. Thus, it has been discovered that the radiative zone rotates more uniformly than the convective zone, suggesting a partial decoupling between these two regions and possible shear at their boundary. This nuanced image of the solar interior is complemented by heliosismology in general, associating gravitational modes with others, such as acoustic waves. But in the radiative zone, it is indeed these subtle oscillations that lift the veil on internal dynamics. The results expected for 2024 and 2025 should refine our understanding of this slow internal rotation in connection with the revision of opal opacities and space missions collecting increasingly precise measurements. Let us return to the evocative photon marathon, this striking metaphor illustrating the extraordinary duration of a photon's journey. Imagine a ray of light born in the very hot depths above the core, embarking on a race to illuminate, much later, the surface. It does not move in a straight line. It is caught in a whirlwind of incessant collisions, absorbed, re-emitted, sometimes doubled or changed in energy, with an astonishing frequency. Each interaction makes it lose memory of its initial direction, and it sets off again at random, sometimes toward the boundary of the radiative zone, sometimes toward the core, in a random walk comparable to a stroll in an opaque cloud. This process demonstrates how light, though reputedly fast, can be delayed by such a dense medium. Outside any matter, a photon would take about 8 minutes to cover the distance from the Sun to Earth. Inside the Sun, this same photon would need about 170,000 years to emerge from the upper layers to the surface, where the probability of escaping into space becomes higher. At each stage, the density decreases, the matter becomes less suffocating, and finally, the photon continues its journey toward the convective zone before reaching the photosphere. From a thermodynamic and nuclear perspective, this radiative zone acts as a buffer between the most energetic region, the core, and the cooler part of the envelope. The temperature here still reaches several million degrees, though it is slightly lower than that of the core, which exceeds 10 million degrees. The pressure remains colossal, as the weight of the upper layers compresses the underlying matter. Yet, it is only by delving deeper, to about a quarter of the solar radius, 174,000 kilometers or 108,000 miles from the center, that one leaves the radiative zone to enter the ardent core of the Sun. This transition occurs around 0.25 times the solar radius from the center. If you were to trace a river to its source, you would be almost at the origin, the thermonuclear core, where hydrogen fuses into helium and other elements, releasing the colossal energy that sustains the Sun. Before reaching this core, one must cross the lower boundary of the radiative zone, where internal rotation sometimes behaves differently from that of the outer layers, and where opacity, linked to iron, has already significantly modulated the path of photons since their birth. Thus, as we approach this boundary, we leave behind the universe of radiative transport to enter the even more extreme conditions of the core. The latest models, updated in 2024 with the new opal tables, incorporate high-precision spectroscopic measurements to refine our understanding of opacity and describe the internal production of light. Researchers, thanks also to the subtle signals of gravitational oscillations, hope to determine the exact rotation speed of the radiative zone and understand in detail how energy is transmitted from the core to the surface. All of this has consequences for estimating the Sun's remaining lifespan, its energy balance, and our knowledge of the evolution of solar-type stars. Through this theoretical journey, we better grasp the importance of this great sea of radiation. It is not a detail. It is the long corridor that connects the nuclear hearth to the turbulent upper layers. In the radiative zone, light experiences a considerable delay. A photon is born in prehistoric times and reaches the upper layer of the Sun only much later. This is exactly what happens. Finally, by crossing this curtain of incandescent plasma, we approach the threshold of the thermonuclear core, where hydrogen fuses to generate the colossal energy that will fuel the star for billions of years. Here, photons change their production regime, gravitational modes collapse into even more complex configurations, and internal rotation may still hold some secrets. But at this stage, remember that the radiative zone has left its unique mark on the energy rising to the surface. A long journey made of incessant bounces, a delicate transport governed by the opacity of iron and other elements, and a rotation more regular than at the surface. In the end, understanding the radiative zone is to understand a vast section of the sun's internal life. It is here that the plasma slows down the frenetic race of photons, preserves the rotational regularity of the star, and prepares the exit of light rays to the convective zone, then the photosphere and space. The photonic marathon is not just an image, it is a reality that reminds us of the complexity of the star that lights our days. And now, after this dive into the heart of the radiative zone, we are ready to cross the most intimate threshold of our sun, the thermonuclear core, where it all begins. Imagine descending to the heart of the sun, into depths so extreme that light takes centuries to find its way to the surface. Here we are in the most secret zone of our star, the core. Their conditions are almost inconceivable. The temperature exceeds 15 million degrees Celsius, 27 million degrees Fahrenheit, and the crushing pressure brings the density to 150 grams per cubic centimeter, 9 pounds per cubic inch. In other words, a cubic centimeter of this material weighs the equivalent of half a glass of water, even though it is mainly composed of hydrogen and helium. In this furnace, a microscopic dance takes place. The protons, which are the nuclei of hydrogen, collide at prodigious speeds. Normally, their electric charge would repel them, but the extreme heat and pressure in the core allow them to fuse. By fusing, 2 protons first form deuterium, then helium-3, before 2 helium-3 nuclei combine to give helium-4. At each step, they emit neutrinos, positrons, and photons of phenomenal energy. Besides this proton-proton chain, which produces the majority of solar energy, there exists the carbon-nitrogen-oxygen cycle. In this process, carbon, nitrogen, and oxygen play a catalytic role in the fusion of hydrogen into helium. Although it currently generates only about 1% of the sun's energy, this cycle is essential for stellar astrophysics, as it dominates in more massive stars. Even on a solar scale, it influences the production of certain neutrinos, those nearly undetectable particles that pass through matter with almost no interaction. For years, sophisticated experiments have focused on detecting solar neutrinos to verify our fusion models. These particles are produced at the core and escape almost instantly, unlike photons, which will take hundreds of thousands of years to reach the surface. By studying neutrinos, researchers gain an almost immediate insight into the fusion reaction at the sun's center. Between 2023 and 2024, the Borexino experiment in Italy confirmed the flux from the carbon-nitrogen-oxygen cycle. These measurements refined our knowledge of the fraction of elements heavier than helium in the sun, which astrophysicists call metallicity. This parameter is crucial for tracing a star's formation history and evolution, since metallicity influences energy transport inside and long-term luminosity. Borexino's data suggested that the sun may contain slightly more heavy elements than predicted in some models, a subject still debated. On the other hand, the Super Kamiokande experiment in Japan in 2224 refined measurements concerning neutrino oscillations. These particles exist in 3 flavors and transform into one another during their journey, a phenomenon called oscillation. Super Kamiokande refined the parameters of this oscillation, such as the mixing angle called Phi-12 and the squared mass difference. These results contribute to testing the standard model of particle physics and searching for potential phenomena beyond this framework. Neutrinos, due to their properties, are excellent messengers for exploring these theories. At the heart of the Sun, fusion generates a colossal radiation pressure, which is the force of photons bouncing in the solar plasma combined with the pressure of proton, helium, etc. particles. These two pressures counteract the enormous gravitational pull exerted by the Sun's enormous mass. This hydrostatic equilibrium stabilizes the star for billions of years. If the pressure collapsed, the Sun would implode, and if it became too strong, it would expand. Thanks to this balance, the Sun is in the main sequence phase, a stable stage that lasts several billion years, during which the core hydrogen fuses into helium at an almost constant rate. For our star, it is estimated that this central hydrogen reserve will be exhausted in about 5 billion years. When this occurs, energy production will drop, radiation pressure will weaken, gravity will contract the core, and the outer layers will swell. The Sun will become a red giant, capable of engulfing Mercury, perhaps Venus. The Earth, even if not swallowed, will then be subjected to unbearable heat. Its environment will become a blazing desert. After a succession of rearrangements and mass loss into space, the Sun's core will transform into a white dwarf, an extremely dense object roughly the size of the Earth, but so compact that a handful of its material would weigh several tons. This distant future puts our current concerns into perspective, but reminds us that even a stable star like the Sun evolves. The history of understanding nuclear fusion at the heart of the Sun is marked by Hans Bethe. In 1939, he published a pioneering study on the proton-proton chain, shedding light on the source of stellar energy. For his work, he received the Nobel Prize in Physics as he resolved the solar antiquity paradox. If the Sun burned a chemical fuel, it would have lasted only a few thousand years, contradicting geological dating. Nuclear fusion thus unified astrophysics and nuclear physics. Thinking about what goes on in the core invites reflection on the implications for the entire Sun and beyond, for the surrounding space. The entire dynamics of the star, from the sunspots on the surface to the planetary solar wind, originate from the energy released at its center. It's a gigantic circuit. Fusion fuels the pressure, which supports an equilibrium. The movements of plasma, notably loops and magnetic fields, transport this energy and release it gradually outward. Neutrinos, on the other hand, are direct witnesses to these reactions. They provide information not only about the current state of the core, but also about the future evolution of the Sun and any potential exotic phenomena. Mentally moving outward, one leaves the titanic crushing of the core, an ultra-dense field where protons fuse, to find less dense zones, the radiative zone, the convective zone, then the visible surface. There, the light born in the heart finally escapes into space after a journey of several hundreds of thousands of years, while neutrinos depart almost instantaneously, carrying the signature of fusion. This plunge into the core concludes our most intimate visit to the Sun and reveals the incredible power required to sustain a star of this size for over 10 billion years. This thermonuclear engine operates with remarkable efficiency and consistency. Fusion overcomes electrostatic repulsion, gravity balances the pressure, and the Sun, thus stabilized, provides heat and light to the entire solar system. Leaving these infernal conditions, we remember that the Sun is just one star among hundreds of billions in our galaxy, each with its own core. The principles of stellar fusion are universal, although the details vary according to mass, chemical composition, and age. our Sun enjoys an almost perfect balance to sustain life on Earth, located 150 million kilometers or 93 million miles away. A somewhat more massive star would have fused faster and had a shorter life cycle, while a less massive star would not have maintained such a stable flow of heat. As science progresses, the study of the solar core gains significance. It informs us about the exact nature of nuclear reactions, the precise chemical composition of the Sun, and the circulation of energy. Research on neutrinos improves, particularly in measuring the flux from the carbon-nitrogen-oxygen cycle. Giant detectors like Boraxino and Super Kamiokande are refining their ability to distinguish different types of neutrinos, track the slightest variation, and test innovative theories. The enormity of the timescales involved puts our human concerns into perspective. 4.5 billion years old, the Sun will continue to illuminate the Earth for about 5 billion years before its transformation. This provides us a considerable margin, even if, for science, the prospect of the red giant invites reflection on the details of this transition. How will the Sun shift from the main sequence to the red giant phase? How will the residual energy be expelled, and in what form? How much mass will be lost during the final pulsations? These questions about stellar end-of-life are linked to our understanding of core fusion. In any case, this visit to the solar core is a temporal journey made possible by theoretical advances and the ingenuity of neutrino experiments. Seeing through the Sun is remarkable. Classical light waves are stopped by the plasma, while the nearly elusive neutrinos allow us virtually to access the fusion zone. We owe these ghostly particles the privilege of exploring the solar nuclear reactor. Solar astrophysics, far from being static, continues to thrive. Future space missions could carry modular instruments measuring every parcel of energetic influence. Advances in neutrino detectors, coupled with the improvement of solar spectroscopy, could further revolutionize our understanding. Debates on metallicity, fusion yields, or possible deviations from known laws will keep animating the scientific community, for even after centuries of observations, the incandescent center of our star holds its mysteries. Ultimately, understanding the core means uncovering a cosmic engine that produces an incredible amount of energy, without which there would be neither light nor heat, and thus no life on Earth. Paying tribute to Hans Bethe and all the researchers who have unveiled the identity of our star is to recognize the importance of this nuclear heart. Now, we leave behind the most fiery zone of the Sun. As we ascend towards the upper layers, we can imagine the series of transformations reserved for the energy released in the core. Each photon resulting from fusion embarks on a long journey through the radiative zone, then the convective zone, before finally escaping into space and traveling 93 million miles until it reaches the Earth. The neutrinos, on the other hand, have already flown straight through, carrying the signature of the fusion. And, in a distant future, when the main fuel runs out, the Sun will transform into a red giant, then into a white dwarf, before slowly fading away. Everything originates from this boiling core. It is the forge that has shaped our solar system and sustains it day after day, from its origins to its destiny. The Sun's magnetic cycles, which shape space weather, offer a spectacle both regular and mysterious. Imagine observing the surface of our star over the years. Dark spots appear, grow, and then disappear, indicative of the internal magnetic agitation. In an average cycle of about 11 years, known as the Schwabe cycle, these spots move from a minimum, where they become scarce, to a maximum, where they abound before decreasing again. Beyond this rhythm, a longer cycle, called the Hale cycle, runs for about 22 years and includes a total inversion of the solar magnetic polarity. Invisible to the naked eye, this inversion demonstrates that the magnetic field renews itself according to a fascinating cyclical calendar. To give a concrete example, the history of astronomy mentions extreme variations in these cycles. The Maunder minimum, named after astronomers Annie Russell Maunder and Edward Walter Maunder, lasted from the late 17th to the early 18th century. During this period, sunspots almost disappeared for several decades. Observations from that time report a sun astonishingly devoid of visible eruptions. Some specialists associate this phenomenon with a marked winter cooling in Europe called the Little Ice Age, although the climatic causes are multiple and not solely solar. Whatever the case, this grand minimum shows that the sun's magnetic activity can decline for extended periods, with sometimes notable consequences on Earth. Moving forward to 2025. According to recent observations and forecasts, solar cycle 25 is proving to be more intense than expected. Instead of a slight rebound, there is a marked increase in the number of sunspots and a heightened probability of violent eruptions. Scientific teams are closely monitoring this phenomenon, as these activity peaks can disrupt our terrestrial and space infrastructures. High solar activity can induce currents in high-voltage lines, risking disruptions to power grids. It can also interfere with the geolocation signals used by GPS systems, as radio waves are deflected or scrambled in a boiling ionosphere. By extension, telecommunications operators fear outages and disruptions in a world where connectivity is central. To understand the origin of these disturbances, let's focus on the most spectacular phenomena of solar magnetic activity: high-amplitude eruptions, classified as Category X, and coronal mass ejections. These two events are related. A solar flare suddenly releases a large amount of magnetic energy at the surface, while a coronal mass ejection projects an immense cloud of charged plasma and magnetic field into space. If this cloud is directed towards Earth, it strikes the magnetosphere and triggers intense geomagnetic storms. In the upper atmosphere, it's the promise of magnificent polar auroras. But regarding power grids, it's the risk of massive outages if managers do not take precautions. Part of the scientific explanation for these violent eruptions is based on magnetorotational instability, a concept in fluid dynamics and magnetism. Initially studied to understand the accretion disks around stars and black holes, this phenomenon also occurs within the Sun. Recent data from the Parker Solar Probe, combined with theoretical analyses, suggest that areas of magnetic shear in the Sun can amplify fields until they saturate, causing sudden eruptions. It's somewhat like a fluid in differential rotation, where magnetic tensions accumulate until they become unstable. The sudden release of this energy manifests as a solar flare and, eventually, a coronal mass ejection. In the face of these risks, the scientific community and space agencies have set up forecasting and monitoring programs. In the United States, the National Oceanic and Atmospheric Administration, NOAA, houses the Space Weather Prediction Center. Thanks to a network of observation satellites and sophisticated mathematical models, this center tries to detect and predict the arrival of solar storms in order to alert satellite operators, power grid managers, and airlines. The goal is to minimize the impact of solar activity on our daily lives and critical infrastructures as much as possible. In Europe, the European Space Agency is preparing the Vigil mission, scheduled for 2029, which will observe in near real time the eruptions on the solar limb, that is, the visible edge of the Sun, to obtain early warnings of a potential coronal mass ejection directed towards Earth. In this context of increased vigilance, it is important to remember that we have not always benefited from such alert means. The most famous event remains the Carrington Storm in 1859, named after astronomer Richard Christopher Carrington. At the time, the telegraph was the dominant technology, and during this storm, telegraph lines burst into flames, sometimes simultaneously in several offices. The currents induced by the sudden increase in Earth's magnetic activity generated sparks, evoking terror and fascination. Some historians compare these early scrambled messages to a first tweet from space, showing how much solar activity can disrupt our communication systems, then and now. Today, as our networks are more interconnected than ever, our vulnerabilities to space weather have multiplied. GPS satellites, essential for guiding planes, ships, cars, and pedestrians, see their signals distorted or delayed by a disturbed ionosphere. Very high voltage lines, which carry energy over hundreds or even thousands of kilometers, hundreds or even thousands of miles, are exposed to geomagnetic storms that can induce parasitic currents. Telecommunications satellite operators continuously monitor their fleet in orbit. Without vigilance, some devices risk overheating or being put out of service during the most intense episodes. Multiple sectors, from aviation to space exploration, now depend on our understanding of the solar cycle and its whims. To forecast these disruptions, experts combine several techniques. First, they continuously observe the sun via space telescopes and images in different wavelengths. The study of sunspots provides an early clue. The larger and more numerous they are, the higher the risk of eruption. They then scrutinize the solar corona, this burning envelope that extends far beyond the visible surface, to identify unstable areas that might release a cloud of plasma. Finally, they use in situ sensors, carried on probes like Parker's Solar Probe or Solar Orbiter, to measure the speed and density of the charged particle flux. These data feed into numerical models aiming to predict, a few hours to a few days in advance, the occurrence of a solar storm and its approximate intensity. In the current context, where solar cycle number 25, expected between 2024 and 2026, is taking on a greater scale than anticipated, international coordination is becoming crucial. Scientific organizations share their information to rapidly disseminate alerts to the relevant sectors. Power companies can then adjust the configuration of their networks or reduce the load on certain lines if a storm is imminent. Satellite operators can put some sensitive instruments into standby mode to limit damage. Astronauts on board low-orbit stations are advised to take refuge in isolated modules to protect themselves from energetic particles. This reactivity, implemented by space agencies and space weather services, clearly shows the awareness of the potential strength of the solar cycle. It's likely that, in the near future, the continuous improvement of instruments will offer us a finer understanding of the mechanisms of these cycles. We will then be better able to anticipate the disruptions threatening our power grids, transportation, satellites, and telecommunications. The study of solar magnetic cycles appears as a safeguard against the unknown. In a world where electronics and data networks govern our lives, a single major solar eruption could create unprecedented global chaos. Aware of this risk, space weather specialists and governments are combining their efforts to strengthen the resilience of our technologies. These measures confirm that the sun, despite its distance, remains the source of phenomena capable of disproportionately disrupting the Earth. A solid understanding of its cycles will thus be our best asset for exploring space, preserving our infrastructure, and ultimately, mastering the majestic power of our star. Mercury and Venus are two fascinating stops for those who want to understand the sun's influence on the space environment. They each offer, in their own way, an insight into the interactions between light, solar wind, and planetary matter. At first glance, these two worlds seem very different in nature and surface conditions. However, upon closer observation, one can detect phenomena closely related to solar activity, the charged particles that flood space, and the planetary reactions that result. In this imaginary journey, we will first fly over Mercury, the small planet closest to the Sun, before heading to Venus, a sulfurous neighbor with a dense atmosphere. Each of these celestial bodies serves as a natural laboratory to study the exchanges between the Sun and any planetary body within its reach. Mercury, the first stop from the Sun, orbits about 58 million kilometers or 36 million miles away. This extreme proximity makes it a privileged witness to the solar wind's assaults, this continuous flow of protons and electrons launched from the Sun's surface at more than 400 kilometers per second, or about 250 miles per second. Without a thick atmosphere, Mercury possesses only a very thin exosphere. This outer layer, so light it seems almost absent, is easily penetrated by the solar wind, which interacts directly with the surface and this thin bubble of gas. To study this exosphere, NASA's MESSENGER missions and Bepi-Colombo and ESA-JAXA collaboration have been crucial. MESSENGER orbited Mercury from 2011 to 2015, producing numerous images and data on the surface composition. It highlighted surprising magnetic variations and mapped hot poles, regions where the temperature peaks when the Sun is at its zenith. Launched in 2018, Bepi-Colombo aims to further uncover the mysteries of Mercury's magnetosphere. The term magnetosphere refers to the area where a planet's internal magnetic field dominates and deflects solar particles. However, Mercury's is weak and asymmetric, with strange deviations in the magnetic field lines suggesting a direct interaction between the metallic core and the solar flux. Due to its proximity, Mercury experiences enormous temperature variations between day and night, over 400 degrees Celsius or 752 degrees Celsius on the exposed side, and about 170 degrees Celsius or 274 degrees on the night side. Without an atmosphere to redistribute the heat, each hemisphere experiences scorching heat or frigid cold, making Mercury an exceptional subject for thermal study. At the same time, the solar wind constantly strips away some atoms and molecules from the surface, continuously shaping the exosphere and revealing its composition. Data from MESSENGER and Bepi-Colombo allow scientists to track these exchanges. They observe, for example, how sodium, potassium, or calcium disperse before being carried away or falling back to the surface. These phenomena are thus modeled to extrapolate to the exospheres of other bodies lacking a thick atmosphere, such as some natural satellites. If our journey now turns to Venus, it's because this planet, with a dense carbon dioxide atmosphere, contrasts sharply with Mercury. Venus is about 108 million kilometers, or 67 million miles from the Sun, always within Earth's orbit, making it a useful waypoint for probes aiming to get closer to the Sun. Engineers use gravitational assistance there, or flyby, consisting of skimming past Venus to alter a spacecraft's speed, angle, or inclination without expending much fuel. The Parker Solar Probe, for example, is making multiple flybys between 2018 and 2025 to gradually approach perihelion, its closest point to the Sun, while gathering data on Venus during each passage. These quick visits unveil part of the veil over the hottest planet in the solar system. Venus endures temperatures close to 460 degrees Celsius or 860 degrees on its surface, the result of a runaway greenhouse effect due to its CO2-rich atmosphere. Beyond this heat, its high atmosphere, much cooler, presents a complex dynamic. Violent winds travel across the sulfuric acid cloud cover at several hundred kilometers or miles per hour. Researchers particularly study the shockwaves propagating in the upper layers, sometimes reaching the planet's twilight zones. The Air and Space Museum often represents these flybys to help the public visualize the orbital ballet involving gravitational assistance. In 2024, the Parker Solar Probe teams plan to analyze new data showing the presence of gravity inertial waves, similar to certain fluctuations in the solar corona. These waves, produced by differences in gravity, atmospheric motion, and planetary rotation, move under the combined effect of gravitational force, centrifugal force, and internal fluid dynamics. In Venus's upper atmosphere, it is assumed that the flow of solar particles, combined with the planet's retrograde rotation, could generate or amplify such oscillations. Scientists see a striking analogy here with the gravity inertial plasma waves of the solar corona, suggesting surprising similarities between Venus and a part of the Sun. Thus, despite their differences in size, composition, and environment, Mercury and Venus serve as true laboratories for the study of sun-planet interactions. In the case of Mercury, the absence of a protective atmosphere highlights the direct role of the solar wind that reaches the surface and the internal magnetosphere. The planet acts like a sensitive plate, where the sun's imprints are clearly marked. For Venus, its dense atmosphere behaves like a gigantic chemical and dynamic reactor. The flux of solar particles, the unique rotation, and the high pressure produce wind and wave patterns, reminiscent, all things considered, of those of the solar corona. Comparing Venus to Mercury and the Sun enriches scientific models. Researchers hope to better decipher the circulations of energy and matter in environments subjected to magnetic fields and particle fluxes. Another significant chapter concerning Venus comes from the observation of its transits across the Sun. A transit occurs when Venus, positioned between Earth and the Sun, appears as a black dot crossing the solar disk. In 1761 and 1769, these rare events mobilized the global scientific community. Observers traveled to the farthest corners of the globe to time the planet's passage. By comparing transit times from different locations, they were able to deduce for the first time the Earth-Sun distance, thus laying the foundations of the astronomical unit, which serves to calibrate all distances in the solar system. This major breakthrough linked time, terrestrial distance, and celestial angles to determine the size of our cosmic environment. This historical context underscores the fundamental role of Venus in solar knowledge. Not only did the planet allow the measurement of the Earth-Sun distance, but it continues to provide clues on the evolution of a world under the Sun's influence. From the 18th century's naked-eye observations to today's analyses of sophisticated probes, Venus remains at the heart of a climatic enigma that still intrigues specialists. Its atmosphere, saturated with CO2 and sulfuric acid, illustrates radical evolutions for a planet once comparable to Earth. This Venusian mirror, paralleled with mercurial data, reminds us of the cosmic power at play and the way solar breath shapes the worlds of the solar system. Beyond research, Mercury and Venus remind us of profound historical lessons. The transits of Venus in 1761 and 1769 are the very example of planetary collaboration, surpassing borders and cultures to better situate Earth in the cosmos. They demonstrated that by combining precise measurements with the enthusiasm of expeditions, we push the boundaries of collective knowledge. Today, modern missions perpetuate this heritage, pursuing new objectives. Quantify energy exchanges in the Venusian ionosphere, map the Mercurian magnetosphere in 3D, or detect similarities between planetary waves and those of the solar corona. These two worlds, although so dissimilar, join in the same adventure, deciphering the codes of a sun whose influence extends relentlessly from the deepest core to the heliosphere's confines. In this imaginary journey, between the furnace of Mercury and the clouds of Venus, we realize that every approach, every flyby, and every measurement confirms the universality of physical laws. The tension between solar power and planetary resistance generates chemical reactions, magnetic currents, and brutal heating, comparable in all these spheres. Studying Mercury and Venus is about exploring the diversity of planetary responses to the same energy source, but also understanding how the Sun weaves a unique relationship with each planet, governed by a fundamental logic. Mercury and Venus are thus much more than two stops on the road toward the Sun. They are crucial milestones in our understanding of Sun-planet interactions. Witnesses of a historical scientific epoch and subjects of contemporary observations, they embody the complementarity astronomers need to refine their models. This complementarity, so evident between the mineral vulnerability of Mercury and the Venusian opacity, prepares us to dissect what happens in other corners of the solar system and in the many discovered stellar systems. Each planet helps lift a corner of the veil on the subtleties of a sun more complex than we imagined, as even the smallest particle of our star triggers astonishing choreographies. Thus comes to an end our stage dedicated to these two sentinels of the solar neighborhood, Mercury, marked by its proximity to the Sun, and Venus, hidden under dense clouds in an infernal environment. They remind us that no planet can escape the solar wind, and that even tens of millions of kilometers, about tens of millions of miles, away, its influence remains decisive. While our probes scrutinize these distant lands, we discover more each day about the complex machinery connecting a colossal sun and the worlds that dance around it. From this knowledge, we retain that studying the planets so closely submitted to our star also illuminates the fate of Earth and its shared cosmic history. The heliosphere presents itself as a vast bubble of plasma shaped by the solar wind, this continuous stream of charged particles ejected by the Sun. Although this region may seem abstract, it truly envelops us, protecting Earth and the other planets from interstellar cosmic rays. To appreciate the scope of this cocoon, whose radius extends beyond 120 astronomical units, one unit being about 93 million miles, one must examine the solar wind, its magnetic field, and modern methods of mapping this both little-known and vital zone. Let's start by defining the solar wind. It's a constant flow of charged particles, primarily protons, accompanied by free electrons and, to a lesser extent, helium ions. These particles originate in the solar corona, this outer layer heated to several million degrees Celsius, several million degrees Fahrenheit. Due to this heat and magnetic field, they reach velocities of several hundred kilometers, about several hundred miles, per second, before spreading through space, carrying with them the Sun's magnetic field. This expansion gives rise to the Parker spiral, the solar rotation, which turns every 25 days at the equator and more slowly towards the poles, drags the magnetic field immobilized in the plasma. As the solar wind moves away, the field lines draw helical structures. Near the Sun, this spiral is faint, but the further we venture towards the edges of the solar system, the more it spreads into large loops, These entanglements evolve over the solar cycle, which lasts about 11 years. During active phases, the intensity and geometry of the magnetic field associated with the solar wind change, reshaping the heliosphere's form. The heliospheric bubble extends to the point where the solar wind pressure yields to the pressure of the interstellar medium. This shifting boundary, located beyond 120 astronomical units, or approximately 12 billion miles, depending on variations in interstellar flux, is named the heliopause. The Voyager 1 and Voyager 2 probes crossed it after traveling through a termination shock, the area where the supersonic solar wind slows abruptly before mixing with the external gas. As they passed through, they measured distinct changes in the magnetic field, particle density, and their energies. Voyager 1 thus observed the transition from solar particles to those of interstellar origin, indicating it was entering the galactic sea. This boundary partially protects us from galactic cosmic rays, highly energetic particles from stellar explosions like supernovas. Their flow varies within the galaxy, and their penetration into the heliosphere depends on the magnetic configuration of the solar wind and the sun's activity. These particles interact with Earth's upper atmosphere, and some authors suggest that these interactions, promoting cloud condensation nuclei formation, could influence the climate. This is Svensmark's hypothesis. It proposes that an increased influx of cosmic rays intensifies cloudiness and modifies Earth's radiative balance. Nevertheless, this concept remains controversial, as many climatic factors come into play, complicating the precise quantification of this correlation. To refine our measurements of cosmic ray modulation and better understand the heliosphere, the IMAP Interstellar Mapping and Acceleration Probe mission, scheduled for 2025, aims to study how interstellar particles penetrate the solar system, interact with the solar wind, and leave marks in the energy and chemical distribution. Its instrumentation will allow a more precise mapping of the heliospheric boundary, analyze particle acceleration processes, and link solar activity to variations in interstellar ion density and cosmic ray modulation. Parallelly, past and present missions have already delivered major discoveries. Ulysses, launched in the early 1990s, performed a polar orbit around the Sun, exploring rare regions, the solar poles. It is there, during solar minima, that the fast solar wind is strongest, influencing the shape of the heliospheric magnetic field. Now, Solar Orbiter continues this task by approaching the high solar latitudes to observe with better resolution the magnetic fields, particle jets, and solar flares, thus complementing our knowledge of the evolution of a plasma packet from the Sun to the Earth. The Voyager probes have highlighted an unsuspected complexity. The outer boundary of the heliosphere is not a stationary bubble, but shows distortions. Regions where the interstellar magnetic field penetrates more directly create zones of turbulence, where interstellar particles mix with the solar wind, forming a chaotic interface. These successive layers, from the supersonic zone of the solar wind to interstellar space, show a gigantic interface, sensitive to variations in solar activity or the galactic environment. During a solar minimum, with fewer eruptions and a more stable magnetic field, the heliospheric bubble becomes more peaceful. In contrast, at the solar maximum, intense eruptions and frequent magnetic variations reinforce the internal structures and modify the boundary. Historically, it is fascinating to note that this protective bubble remained unknown to us for so long. Before the space age, a continuous flow of particles was unimaginable. Astronomers had a sense of an interplanetary medium's existence, but were unaware of its density and magnetic field. In the 1960s, the Explorer and Pioneer probes highlighted this stable flow of particles, revealing that our star extends its influence far beyond the Earth-Sun distance of 93 million miles or 150 million kilometers, thus revolutionizing our vision of the solar system. Today, this bubble, the heliosphere, is at the heart of many studies because it forms the first line of defense against high-energy galactic particles. Better understanding it means better knowing how the Earth and its neighbors undergo cosmic vagaries. The missions Ulysses, Solar Orbiter, Parker Solar Probe, Tracing the Origins of the Solar Wind, or IMAP, draw an increasingly precise picture of this adventure of matter and the magnetic field across space. The debate around the Svensmark hypothesis illustrates the importance of this research. The idea that cosmic rays might modulate terrestrial cloudiness remains of interest, particularly for calibrating climate models. Although correlations noted between cosmic rays and cloud cover, or between prolonged solar cycle minima and climatic episodes, have been observed, other factors, such as volcanic emissions, orbital variations, or greenhouse gases, complicate the analysis. Researchers thus remain cautious while continuing their measurements. Ultimately, IMAP's 2025 mapping will help specify the proportion of cosmic rays filtered at the heliospheric boundary. The more we understand the dynamics of this bubble, the more we will know how high-energy particles reach us. We will better distinguish the influence of the solar cycle and how the polarity of the magnetic field affects cosmic rays transport. Moreover, the sun's rotation around the galaxy exposes us to various interstellar clouds, whose density and speed modulate the pressure at the boundary, altering the geometry of the heliosphere. These variations, on very long time scales, could shed light on some past climate changes if astronomers and paleoclimatologists cross their data. Finally, the heliosphere represents an envelope on which the balance of the solar system depends. Dynamic, it reacts to the outbursts of our star and continuously transforms. Interplanetary probes, space mapping missions, and terrestrial instruments collaborate to measure, analyze, and understand this bubble, its influence on Earth and the planets, as well as its interactions with the galaxy. If we imagine Earth as a vessel navigating a cosmic ocean, the heliosphere would be the invisible hull aimed at protecting it from the most violent waves. Exploring how this rampart is constituted, breathes, and communicates with the galactic immensity remains an exciting challenge at the crossroads of astrophysics and climate science. And, considering the complexity of the phenomena, from the solar poles to the boundaries of interstellar plasma, this field of research has many decades of discoveries ahead. Here we are at the heart of a story that takes us far beyond everyday life on Earth. To place the Sun in the vast cosmos, one must first imagine the Milky Way, our galaxy, a gigantic disk formed of hundreds of billions of stars, clouds of gas, dust, and dark matter. From Earth, we only see a luminous band in the sky as we are immersed within it. If we moved far enough away, we would see a huge stellar whirlpool where the Sun appears as a mere point. Yet, understanding the history of the Sun and Earth requires knowing their place and movements within this rotating structure. The Milky Way resembles a flat disk with a central bulge, probably housing a supermassive black hole revealed by the frantic movement of orbiting stars. The most precise measurements indicate that the Sun is about 27,000 light-years, approximately 167,170,000 miles from this center. Remember that a light-year corresponds to the distance traveled by light at about 300,000 kilometers per second, approximately 186,000 to 282 miles per second, in a year of 365 days. Saying that the Sun is 27,000 light-years from the galactic center means it would take 27,000 years to reach this point, traveling at the speed of light, a concept bewildering to our human mind. Our galactic region is called the Orion Arm, or local spur. The spiral arms of the Milky Way are zones where stars, gas, and dust accumulate. The Orion Arm is not one of the main ones, but rather a branch between the Perseus and Sagittarius arms. Its name comes from the constellation of Orion, but it doesn't confine us. It's a celestial geography reference. Like the whole galaxy, this arm rotates, and the position of the Sun within it is constantly changing. The Milky Way spans about 100,000 light-years, approximately 621,371,000 miles in diameter. Although its boundary is blurred, the stellar density gradually decreasing toward the outside. Beyond this disk, a halo of dark matter envelops the galaxy. The Sun, like other stars, moves through this landscape, accomplishing not only a rotation around the galactic center, but also slight oscillations and occasional encounters with other stars or clouds of gas and dust. This motion resembles a cosmic ballet. Astronomers estimate that the Sun orbits around the center of the Milky Way at a speed of about 828,000 kilometers per hour, approximately 514,462 mph. Although this speed seems dizzying, it needs to be put into perspective with the radius of the orbit, which is 27,000 light-years. Despite this pace, it takes a considerable amount of time for the Sun to complete a full revolution around the galactic center. This is called the galactic year. When we speak of the Earth's seasons, we talk about the Earth's revolution around the Sun in 365 days. Similarly, a galactic year refers to the time required for the Sun to complete a full turn of the Milky Way. Estimates vary between 225 and 250 million years due to the complexity of precisely modeling galactic dynamics. Since its formation about 4.5 billion years ago, the Sun has completed only about 20 galactic revolutions, or 20 galactic years. On a human scale, this totally relativizes our perception of time. The appearance, evolution, and diversification of life on Earth occurred while the Sun had not yet completed a full turn. Moreover, the Sun does not strictly evolve in the galactic plane. It performs vertical oscillations, moving up and down through the disk. These back-and-forth motions, which last between 30 and 35 million years, lead it to traverse regions potentially denser in gas and dust. Some researchers suggest that these passages sometimes coincide with a greater frequency of comets and perhaps with periods of increased impacts on Earth. Others propose a correlation with major mass extinctions when life has abruptly declined, but this hypothesis remains highly debated and is not yet confirmed. The galaxy also possesses a vast magnetic field, much more diffuse than that of the Earth, but spread over thousands of light-years. Dynamo mechanisms in the ionized gas of the spiral arms, galactic rotation, as well as shock waves from supernovae, contribute to forging this complex magnetic field. When the Sun traverses a denser spiral arm, the local intensity of this field can vary, which, in turn, modulates the shape and size of the heliosphere, the magnetic bubble that protects us. Depending on the density of the interstellar gas and the strength of the ambient magnetic field, the heliosphere can contract or expand, influencing the flow of cosmic rays reaching Earth and, potentially, the atmosphere and life. Studying this galactic magnetic field is delicate because it is very diffuse. Astronomers use indirect methods such as the polarization of light coming from distant stars, which they compare with numerical simulations to reconstruct the structure of the large-scale force lines. Locally, the Voyager probes, launched more than 40 years ago, have crossed the heliopause and are now directly measuring the interstellar medium. These data provide a first glimpse of the impact of the galactic magnetic field on our solar system. Thus, placing the Sun in our galaxy reveals its role as a mere galactic traveler, engaged in a loop around the center, oscillating through the plane, and traversing a varying interstellar medium. This star, compared to the hundreds of billions of others, appears modest, even though it is vital for us. Every blade of grass, every mountain or ocean on Earth is linked to this cosmic dance. When we look up at the Milky Way, we glimpse a tiny fraction of this gigantic puzzle. While the Sun is just a single bright spot in the night, it remains the pillar of our existence, tracing its path for billions of years and continuing its dance within the shimmering spiral of the Milky Way. Imagine a vast cloud of gas and dust floating in the interstellar darkness. Long before the appearance of life on Earth, such a cloud, carried by the spiral arms of the Milky Way, bathed in a region still unknown to our distant ancestors. Mainly composed of hydrogen and dust grains, rich in carbon, oxygen, silicates, and some metals, it seemed tranquil. Yet, an incredible story was about to unfold, the birth of our Sun. In this narrative, we go back nearly 4,600,000,000 years to detail how cosmic forces forged the star that illuminates us today. This cloud, known as a molecular cloud, contained mainly hydrogen, the most abundant element in the universe. Each atom, consisting of a proton and an electron, was accompanied by helium and dust, rich in carbon, oxygen, silicates, and a few metals. These clouds are scattered along the spurs of the spiral arms, including the one where our solar system is located, the Orion Arm. However, a cloud does not always become a star. A triggering event is needed to locally densify the gas until gravity overcomes the natural tendency of the cloud to disperse. In the case of our future Sun, astrophysicists believe that a nearby supernova triggered this process. A massive star at the end of its life exploded, sending a shockwave that compressed a portion of the hydrogen and dust cloud. With this sudden compression, local density increased and gravity gradually took over, causing a progressive collapse. The more the matter tightened, the more gravity attracted surrounding gas, forming a central condensation that was to become the heart of the future star. By studying very ancient meteorites, researchers have discovered radioactive isotopes, notably aluminum-26 and iron-60, typically produced by a supernova. These isotopes, unstable on a cosmic scale, attest to the enrichment of the primordial cloud in heavy elements. Their presence in the first solids of the solar system indicates that the nearby supernova not only triggered the collapse, but also sowed effervescent chemical traces in the primitive matter, irrefutable proof that the violent death of a star paved the way for the birth of the Sun. At the center of the contracting region, density and temperature rose, forming a protostar still cold at its core, but warmed by compression. Around it, the residual matter organized into a rotating protoplanetary disk, a consequence of the conservation of initial angular momentum. This disk, a mix of gas and dust grains, became the cradle of the planets. The grains gradually clumped together to form pebbles, then planetesimals, and finally planet-sized bodies. At the center, the temperature eventually reached several million degrees, triggering the fusion of hydrogen into helium and transforming the protostar into a full-fledged star, the Sun. The nascent solar winds dispersed the residual gas, leaving the dense elements to condense close to the star, forming rocky planets, while the cooler outer regions gave rise to the gas giants. Stars rarely form in isolation. The collapses of the initial molecular cloud occurred at several points, forming an open cluster, including the solar fetus and its multiple stellar sisters. For hundreds of millions of years, these stars evolved together, some becoming red dwarfs, others more massive stars. Then, under the influence of galactic gravitational forces and mutual interactions, the cluster dispersed. Members of this sibling group took different directions in the Milky Way while maintaining the same chemical compositions, an indelible heritage of their common origin. To try to find these solar sisters, astronomers practice chemical tagging. They analyze the light of stars to extract their spectral signatures, true chemical fingerprints made up of heavy elements like iron, calcium, or silicon. A star whose chemical composition is identical to that of the Sun and whose age is comparable has a high probability of having emerged from the same primordial cloud. Thanks to vast catalogs, such as those created by the Gaia mission, teams of researchers systematically compare the spectra of stars to detect those sharing our stellar DNA and thus reconstruct the Sun's family tree in the galaxy. When you look at the Sun, you often forget that it is the product of a long cosmic history. From the initial compression of the molecular cloud under the impulse of a supernova to the ignition of the fusion core, each step shaped the solar system. The isotopes discovered in meteorites, emanating from that distant explosion, are like silent witnesses of a cosmic violence that yet gave birth to a stable star, capable of sustaining life on the small blue planet. All the atoms that make up our body once traveled in this journey. From interstellar dust to Earth, they have traversed a fascinating celestial epic. Today, our space and ground-based telescopes constantly survey the stars of the Milky Way. The Gaia mission maps the position and movement of 1 billion stars, while spectrographs record their chemical signatures. Each star, whose composition coincides with that of the Sun, brings us a little closer to understanding our origins. Finding even one stellar sister is like reconstructing part of the Sun's childhood and understanding how our star has evolved from its birth to its current location, 27,000 light-years from the galactic center. The story of the Sun's formation is written like a cosmic poem, a dark cloud awakened by the shockwave of a supernova, a collapse where gravity reigns supreme, the birth of a protostar with an incandescent heart, the formation of a proto-planetary disk, the emergence of planets, and the dispersal of a stellar family. Then the Sun became calm enough to allow the blossoming of a biosphere on Earth. All of this would have been impossible without the initial supernova and without the laws of gravity and rotation, which sculpted this primitive landscape. Understanding the birth of the Sun, therefore, is to tell a shared story where every fundamental physical phenomenon and every dynamic has played a role. Long before humanity questioned its origins, the universe was experimenting with the mechanisms of life and death of stars. Each supernova enriched the interstellar medium, preparing the next generation of stars. Today, we continue this quest, thanks to advanced instruments, giant telescopes, and space missions ready to detect the most subtle of chemical imprints. If one had to remember a single idea from this adventure, it would be that we all come from unimaginable cosmic processes that occurred long before the birth of humanity. Every time we feel the warmth of the Sun on our skin, let us remember that this star is the result of a precise sequence, a cloud compressed by a shockwave, an incandescent core becoming a star, a protoplanetary disk brimming with future worlds and stellar sisters scattered across the Milky Way. Our atoms, once interstellar dust, tell this fabulous cosmic epic, reminding us that, although modest on the scale of the galaxy, our stellar history is unique and unfinished. Imagine yourself in the immensity of interstellar space, just far enough to contemplate a multitude of bright points against a black background. Among these stars, our Sun seems unique and indispensable to life on Earth, but in the Milky Way, it is just a point among hundreds of billions of stars. It is neither the most massive, nor the brightest, nor the most eccentric, but its characteristics are remarkably balanced. We will discover how the Sun ranks among the stars, why it is called a yellow dwarf, and how astronomers place it in the Hertzsprung-Russell diagram. We will also see how its gravitational balance shapes the destiny of the solar system up to the Oort cloud, and we will mention the cultural influence of this stable star, which has contributed to the emergence of our civilization. When classifying stars, they are sorted according to their surface temperature and luminosity. Our Sun is called a yellow dwarf, a term that may surprise since from Earth, it appears rather white. The atmosphere and the sensitivity of our eyes alter its hue. Seen from space, it would be white with a slight tint of yellow. Its technical designation is spectral type G2V. The letter G indicates a moderate surface temperature around 5,800 degrees Celsius, 5,800 degrees or 10 to the 492 degrees. The number 2 specifies its level of luminosity among G-type stars, and the letter V means it belongs to the main sequence. This means it draws its energy from hydrogen fusion, a stable phase lasting about 10 billion years. In short, yellow dwarf denotes an average-sized and temperature star with no extreme characteristics, but its luminosity exceeds about 90% of the stars in the galaxy because the majority are small red dwarfs, less hot and less bright. To better see its place among the stars, let's compare it to some famous giants. Sirius A, for example, is hotter and more massive, a Type A star brighter than the Sun. Betelgeuse, a red supergiant visible in Orion, has a radius so large it would engulf Earth if it occupied our position. It shines intensely but unstably, as its nuclear fuel reserves are depleting. Conversely, the majority of stars in the Milky Way are red dwarfs, smaller and cooler than the Sun, and so dim that they are only noticed when they're very close. The Sun occupies an intermediate position, neither a flamboyant supergiant nor a discrete red dwarf. It offers stable energy over several billion years, otherwise too short for the emergence and evolution of life. Astronomers use the Hertzsprung-Russell diagram to classify and predict the evolution of stars, a kind of map where each star is placed according to its luminosity and surface temperature. On this graph, the temperature decreases from left to right and luminosity increases upwards. The Sun is located in the middle of the main sequence, a zone reserved for stable stars that fuse hydrogen. Hotter stars are placed to the left, cooler ones to the right. At the top are the giants and supergiants, more luminous and often cooler like Betelgeuse. At the bottom are the red dwarfs, cooler and less bright than the Sun. This median position confirms that the Sun is halfway through its life, with about 5 billion years left before becoming a red giant and disrupting the solar system. Beyond this classification, the Sun plays a central role in the solar system. Its gravity keeps all the planets in orbit, from Mercury to the distant reaches of the Oort cloud, tens of thousands of astronomical units, or over millions of miles away. With more than 99% of the total mass of the system, it anchors the gravitational cohesion. Its luminosity, relatively constant, despite an 11-year cycle marked by the appearance of sunspots, has never irreparably disturbed the Earth's climate. This stability has allowed for the appearance, evolution, and diversification of life without suffering from sudden bursts of deadly radiation or abrupt drops in energy. On a human scale, this persistent solar energy calm has ensured a climate suitable for agriculture, ecosystems, and civilizations. Throughout time, humanity has worshipped the sun, seeing it sometimes as a god, sometimes as an essential cosmic center. The Egyptians called it Ra, the Greeks Helios, the Norse Sol. Then, science revealed its true nature, a ball of fusing gas, mainly hydrogen and helium, balanced by gravity. This paradox of an object both ordinary and vital is fascinating. Although it is less spectacular than a supergiant, its energetic constancy over billions of years has allowed the rise of complex ecosystems and the birth of a technological civilization. Without its regular cycles, without its light, no plants, animals, or humans could exist. In this chapter, dedicated to the galactic future of the Sun, we explore the stages that await it when it leaves the main sequence and stops fusing hydrogen. For more than 4 billion years, it has kept the Earth bathed in light and heat. But in about 5 billion years, its central hydrogen will be exhausted. At that time, the internal balance will change. The core, enriched with helium, will contract, while the outer layers expand, initiating the spectacular transformation into a red giant. The transformation into a red giant will result in a considerable swelling of the Sun and upheaval of its close environment. As its core contracts in an attempt to fuse helium, the outer envelope will extend, surely engulfing Mercury and probably Venus. Although Earth remains in orbit, the extreme heat will evaporate its oceans, strip its atmosphere, and annihilate all forms of life. After this blazing gigantism, the fusion of helium will cease, and the outer layers, having become unstable, will be expelled into space, forming a planetary nebula. Far from being planets, these bubbles of incandescent gas and dust, illuminated by the residual core, offer a colorful spectacle, from red to green, produced by the heated elements. Although ephemeral, this cloud will remain the ultimate visible manifestation of our star. Within this nebula, the Sun's core will become a white dwarf, an ultra-dense Earth-sized sphere retaining a notable fraction of its mass, supported by electron degeneracy pressure. Burning at several 100,000 degrees, it will shine from its residual heat before slowly cooling over billions of years, ending any solar wind or intense radiation. From a galactic point of view, this white dwarf will continue its orbit around the center of the Milky Way, itself located tens of thousands of light years, or over millions of miles, and completed in over 200 million years. In about 4 billion years, the collision with the Andromeda Galaxy will disrupt spiral arms and stellar clouds. The little white dwarf may then be drawn into new flows, or integrated into clusters born from this fusion. Chemically, the Sun, through its nuclear reactions, will have produced elements heavier than hydrogen, gradually enriching the interstellar medium. During the nebula phase, these expelled layers will carry gas and dust, while the solar wind will have already scattered particles to the edges of the system. Thanks to this galactic recycling, these atoms will contribute to the formation of future stars or planets, making the Sun an essential link in the great cosmic chain. On a human scale, these transformations surpass any direct experience. 5 billion years far exceed the antiquity of humanity, making our civilizations almost instantaneous in the face of these stellar cycles. Yet science allows us to model this destiny thanks to physical laws, telescopes, and space probes. By comparing the properties of different stars, we confirm that the sequence of main sequence, red giant, planetary nebula, white dwarf, is a scenario solidly supported by observation. In the shorter term, one can imagine that a sufficiently advanced civilization might try to anticipate these upheavals. If our species, or one of its descendants, survives for millions of years, it could migrate to safer areas of the galaxy before the sun becomes a red furnace. Some already predict that a gradual increase in its luminosity will render Earth uninhabitable, urging the relocation or terraforming of other bodies beyond Mars or in other systems. This vision remains theoretical, as our urgent challenge is to preserve Earth in the face of current environmental changes.